We've been talking about partial pressures. Partial pressures have application in deep sea diving, which is probably not a sport that many of us engage in, but it's still kind of interesting. So our lungs perform best when the oxygen partial pressure is 0.21 atmospheres. This is air at sea level. So this is where we perform the best. At higher elevations, the total pressure decreases. You go up into the mountains, the total pressure decreases, and the partial pressure of oxygen also decreases. This is why last summer when we were at Rocky Mountain National Park up at the Alpine Visitor Center, it's like 14,000 feet above sea level, you get all breathless and stuff just walking up a little hill because there's just not as much oxygen there, because there's not as much air. Hypoxia is the word that describes a condition of oxygen starvation. You're just not getting enough oxygen to even really survive. Severe hypoxia, pressures of less than 0.1 atmospheres of oxygen, can result in death. So here's the range. Safe is anywhere from 0.21 air at the surface up to a maximum of about 1.4 if you're exerting yourself, or 1.6 at rest. Above that, you get into oxygen toxicity. Below that level of oxygen, it's hypoxia, oxygen starvation. So above about 1.4 atmospheres, oxygen toxicity. So we need oxygen to live, right? But oxygen can be toxic. We need water to live, but too much water can be toxic. I'm just trying to give people a perspective. We get all concerned about chemical additives in our food and things that we can't pronounce on labels, but everything is a chemical. Everything has a chemical name that somebody can't pronounce. Anything can be toxic at too high of a level. So we just have to calm down a little bit with all that hysteria of stuff in your food. Oxygen toxicity. You get twitching, tunnel vision, and convulsions. Now, are you going to encounter oxygen toxicity just running around Fresno? No, you're not. There's no high pressure oxygen just out there lurking around a bush trying to get at you. But if you're diving and breathing pressurized air, this could be a problem. So too much oxygen is bad. Pressurized air, the total pressure is increased, the pressure of oxygen is increased, the pressure of nitrogen is also increased. And so nitrogen can also be toxic. It's called nitrogen narcosis, or rapture of the deep. They say it feels similar to being tipsy or slightly drunk, which, it's like, well, maybe that's a feeling you like. But if you're several meters underwater, is feeling somewhat drunk a wise thing? No, it isn't, because your judgment is also impaired. So deep sea divers who are going below 50 meters use specialized mixtures of gases so that they don't encounter oxygen toxicity or nitrogen narcosis. One of these is called heliox, which is a mixture of helium and oxygen. So the helium replaces nitrogen so that you don't encounter this nitrogen narcosis. So we could solve a problem like this. A diver breathing heliox with an oxygen composition of 5% wants to adjust the total pressure so that the pressure of oxygen is 0.21 atmospheres. What total pressure does this diver need? We look at that and we think, where do we even start with this? Because it's been a whole week since we looked at anything like this. What we need to remember is that the partial pressure of the oxygen is going to equal the fraction of oxygen in the mixture times the total pressure. So 5% of this gas is oxygen. That means that oxygen exerts 5% of the total pressure. So we need to figure out what should the total pressure be if we want the partial pressure of oxygen to be 0.21. So this is 0.21. The fraction is the percentage divided by 100. So the fraction is 0.5, and we want to find the total pressure. So we need to rearrange this equation. The total pressure, I'm having stylus issues here. The total pressure is going to be the partial pressure of oxygen divided by that fraction of oxygen. The total pressure, the partial pressure of oxygen is 0.21 atmospheres. And the fraction, 5% divided by 100 is 0.05. Let's get out my calculator. 0.21 divided by 0.05 is 4.2. So the total pressure needs to be 4.2 atmospheres. Any questions? So this idea, collecting gases over water, is more important. We did this in lab last week. When we collect a gas by bubbling it through water, the water molecules become mixed with the gas molecules. Another way to think of it is that if we have water here, as the hydrogen in this example displaces the water and the water goes down, some of this water is going to evaporate into this space that's being made. And so in this container, we have the hydrogen gas that we're collecting and they're looking at, but we also have water vapor. And this is a wet gas because it's mixed with water. If you have sand and you mix it with some water, you have wet sand. So in the lab, what was confusing to a lot of people was it was asking, what's the pressure of the dry gas? Well, that's the gas without the water. So we want just the pressure of the hydrogen and not the pressure of the water vapor. The water vapor pressure, it's often called just the vapor pressure of water, depends only on the temperature at which the gas is collected. If the water is warmer, there'll be a higher vapor pressure. If the water is colder, there'll be a lower pressure. And so what we did in lab is we just looked it up in the CRC, that big book. So here's a simplified vapor pressure of water table. So this is just giving every 10 degrees, and we see that as the temperature increases, the vapor pressure increases as well. So if we collect hydrogen gas over water, with a total pressure of 758 millimeters of mercury, a temperature of 25 degrees Celsius, what's the partial pressure of the hydrogen gas? This uses Dalton's law of partial pressures. The total pressure is going to equal the pressure of the hydrogen plus the pressure of the water. The total pressure is the pressure of each of the gases added together. We want to find this one. And so rearranging this equation involves subtracting the pressure of the hydrogen equals the pressure of the total minus the pressure of the water. The total pressure was given to us. The water pressure, we look it up. Here's 25 degrees. At 25 degrees, the vapor pressure of water is 23.8. This is in millimeters of mercury, and this is in millimeters of mercury. So we have 758 millimeters of mercury minus This one right here, to 23.8. millimeters of mercury. 758 minus 23.8. This latest iOS update has not done nice things to my iPad. If we're looking at significant figures, this one had uncertainty in the ones place. This is in the tenths place. So we're going to go with the larger uncertainty, and we're going to round our answer to 734. Any questions?